that last factor? And what did we say yesterday that last factor is? From your notes or just knowing? N minus, P minus N minus 1, which is, in this case, negative 1/3 minus N minus 1. You follow? Okay, now, here we go. In this case, we're trying to estimate the cube, 1 over the cube root of 1.2, which, translating it to a more useful form, doesn't that mean we're trying to figure out what 1 plus 0.2 to the negative 1/3 is? And that means we're basically trying to use this binomial with an x of 0.2 or 1/5, whichever you prefer. I'm going to try 0.2 this time and see if that's better. If you use fractions, that's fine too. M at 0.2 then is 1 plus negative 1/3 of 0.2 plus negative 1/3 of negative 4/3 of 0.2 squared over 2 factorial plus negative 1/3, negative 4/3, negative 7/3, 0.2 cubed over 3 factorial. Don't worry about the general. Are you with me? You stop. I can't go too fast today. If you just would tell me, I'd slow down a little. Okay, so we're cool. Now, the idea then is we need to say, okay, that's how I'm going to estimate it. Now we need to figure out, all right, how many am I going to need to get the precision they're demanding? In this case, they're demanding precision of an error less than 1,000. So, first of all, we say, is this an error-bound kind of case? Is it? Yeah, we'll prove that later. But it is. And so now we need to actually find these guys. And so individually, and probably store them for posterity. So would you get out your calculator and we'll start. I think I'd probably start with the third term. The second term is pretty obvious. Okay, so the third term I believe is negative 1/3, negative 4/3, 0.2 to the third, second, right? Okay, to the second over 2 factorial. This time I think I'm gonna do the factorial because. Okay. All right, did you get 0.008? All right, now, will that serve then as an error bound or not small enough? Not small enough, surely 8 thousandths is bigger than 1,000, so we need to go one more. So you could retype the next term from scratch, or you could recall the previous term, and then just bring in what the next term would have. What would the next term bring in? Negative 7/3, and it'll change to cube, and 3 factorial. That, doggone it, is still not quite small enough. Yes, did I make a mistake or question?
No.
Okay, so that's not quite small enough. We need one more. Let's try one more. So that means shucks, you know what I just forgot to do? I told you to do? That first one that didn't work, I'm going to need these later, so I should have stored that to A. Doggone it. And the other one, as you find these, you should probably store these. Oh, what am I doing? Because after you find the error bound there, you're going to have to go back and add the ones you found, right? All right. So you need to store those as you go. I forgot. Now, going to the next term. My new next derivative factor will be negative 10/3, right? And then the exponent's going to change to 4. And the factorial is going to change to 4. And that feels like it's it. 2 times 10 to the negative 4, which is 2 10,000ths, right? 1 5,000th is less than 1 1,000th. Okay, so that term is my error bound, which means I want to add all the terms before it, right? Okay, so I'm going to add 1 plus negative 1/3 times 0.2. And I think I had an A there, shucks, and a B. And I'm getting 0.94083. Do we agree? Okay. All right then. Now let's talk right up. Let's first declare our answer. 1 over the cube root of 1.2 is approximated by S. Do we use S2, 3, 4? 4. S4, which is 0.9408-ish. Now, we have to also include a little bit of justification to bolster our claim why this error is less than 1,000. Are you with me so far? Okay. So in doing that, we need to meet the conditions and then say this is why because of the error bound. So let's go with, first of all, this M at 0.2 series is an alternating series. I think you'll agree it's alternating. Negative, this is positive, okay? The terms are going to 0. And the terms are decreasing right from the beginning, really. We didn't have to, do any clarification on that. And so because of that, it must be the case that the difference between the true infinite sum S and S4 is less than or equal to the absolute value of 8.5, which is 2 point something times 10 to the negative 4th, and that's less than, finish it, and that's less than 1,000, okay? 1.00. All right, I proved that my error is less than 2 10,000ths, and so yeah, it's less than $1,000. You with me?
Yes.
Okay, would you look at your test then? I'm going to pause this recording. I debated whether to include this part of the lesson because I could probably get to the calculus without it, but I feel like big picture for your math education, it might be good to go over a little bit of combinatorics, all right? So just to remind you of things you learned way back. If I said, how many ways can 7 people be arranged in 3 seats? How would you find it? 7 times 6 times 5. Now, if I were teaching pre-algebra, I would say put spots down for each choice to be made, and then how many choices, and then you multiply, right? If I were teaching this in calculus or pre-calculus, I would say pretend they're all 7 were to be arranged. 7, 6, 5, 4, 3, 2, 1. And then eliminate the ones that don't need to be arranged. I think you'll agree that after I fill the 3C, I then don't go rearranging the people that aren't even chosen, right? So we remove that part. Now formulaically then, you could say that this combination of permutation of 7 things taken 3 at a time is like arranging all 7, but then removing those that are not chosen. Now those that are not chosen was 4 factorial, the left outs, yeah? And generally speaking, NPR, love it, is the top, which is to say arrange all, and remove those that are not chosen. Now if R represents chosen, then how many are not chosen? And minus R. So that's where the formula comes from, and it's useful. And if those of you who are going to be engineers, there's a whole field of probability as applied to engineering. It's really cool, and you'll love it. It involves calculus with probability. So I kind of wish I was you, just to all the things you're going to see. Oh, it's so excited for you. Except you're smarter, so you'll actually understand. So how many different groups? How many different groups of 3 people? Groups are a little different. First of all, we call that combination. We'll go over that. But imagine the same idea. Now, wouldn't you agree I could still say I'm going to arrange all the people and remove the arrangements of those that are chosen. But now I'm going to do one better. Because Emma, Sam, Yulia should not be counted as a different group than Yulia, Sam, Emma, right? Those are the same group. Now, what I have so far is counting them different. This is arrangements. That's counting all of those possible arrangements. So I need to further reduce this by, once I have a group of 3, how many ways can I arrange that group? When I have 3 people, how many ways can I arrange them? 6 times, or 3 factorial, right? Do you agree? Now, I then need to divide this out by 3 factorial, because that then further removes the ways to arrange a group. And I don't care about the arrangements and combinations, all right? So in combinations, generally then, you'll sometimes see this notation, sometimes see this notation, but most often see this notation. It almost looks like a matrix. It's not a fraction, n over r. It's 2 big parentheses, n and r. And I was always taught to read this as n choose r. But I don't know if that's universal, quite frankly. And the formula for that is arrange them all, n factorial, remove those that are not being chosen, n minus r factorial, and also remove the ordering of those that are chosen. That leaves you with groups. That boils it down to an essence of just groups. You with me? All right. Now let's apply this to algebra. A plus b to the first, I shouldn't have put that there, but you get the idea. It's a to the first plus b to the first, right? That's probably what let's put a plus b squared. What is it? All right. Now, it was obvious from the last class that they did not remember the cubic. What is it? 1331. Yes, 1, 3. Now, how do you remember that? Okay, you could do Pascal's triangle, and I love Pascal's triangle. I kind of miss teaching pre-calc just for Pascal's triangle. All so many times. That's a pattern of heaven. But most, especially for in terms of larger cases, if I said find the 78th term of a plus b to the 93rd power, there's no way I'm doing 94 rows of Pascal's triangle. That's crazy. Okay, so you need a quicker way to jump to places that are further down the line. Now, the way to do that is combinations to get those coefficients. And the reasoning is not just because, hey, it'll be fun to use coefficients. Math people don't do things for no reason. There's always a reason. And the reason goes like this. Imagine if your Algebra 1 teacher is just totally crazy. Whoa, I just hit myself with my key. Total crazy whack, and he taught you to distribute like this. I'm going to first take a times a times a. A. I'm not going to use exponents. And then I'm going to take a times b. All right? Now I'm going to start by going AB. AB, A. And AB, B. And it feels like that's all the possibilities with A as the first term. Do you follow me? Then I could start with B. B, A. That. And then B, A, B. And then B, B, A. And then B, B, B. You cool? And then you would typically combine like terms. If they're like terms. Are there like terms? Yeah. How many 2A's and a B terms are there? 3. Now, but are those like terms? They look different. They're the same. Why? But they're all multiplied together, but they're different orders. Oh, so you're telling me order doesn't matter. Oh, there you go. So order doesn't matter means you're looking for groups of 2A's and 1B, where order doesn't matter. And therefore, there are, if I take from 1 to 3 factors, I choose 1B. You could also look at it as 2A. 3 choose 1 and 3 choose 2 are equal. Because it'd be 3 over 1, 2, or 3 over 2, 1. But 3 choose 1 is how many different combinations of 2A's and 1B. And 3 choose 2 is how many different combinations of 1A and 2Bs. And the outsides, there's really, I know this is weird, but it's 3 choose no B's, sorry, and 3 choose 3 B's. All of them are B's. But those are not zeros, they're ones, because 0 factorial is 1 if you got it to 20. Are you with me? Are you with me?
Yes.
A little bit? Okay. Now then, because these all involve these crazy sums, it would be very logical to use summation notation. Now, we hesitate doing this at lower levels because younger students are a little intimidated by the whole summation. Okay, but a plus b to the power is something like a sum, oops, not an infinite sum, a sum of coefficients, an a and a b, right? Now, in terms of the starting index, let's call the power, the starting counter value n, right? Now, which of these exponents, so I'm going to tie it to one of the exponents, which of the exponents, for the a or the b, would it be best to tie into? I'm afraid that question was so wordy it didn't make sense. Look at the exponents of a, they're counting down, yes? Okay. The exponents of b, they're counting up. By summation, we count up. And so what exponent should we tie the counter to? To b, all right? So we're going to say b to the, now b starts, I'm going to say b to the nth power, and b starts to what? What do we start with? How many b's? None, okay? And what does it end at? B ends at the p power, all right? And the coefficient is that every time it's the total power, which in this case is p, choose whatever the b power is a match. So that's the binomial theorem. And those of you who took AP Stat know that that's super duper useful in probability and statistics, right? Let's go, before I go to 1 plus x, now I'm going to blow off, we'll put in the probability later. I got to get to this calculus, okay? So imagine if this was 1 plus x instead. 1 plus x to a power then would be the same deal, but instead of what's the power of n? I never finished it. N to the what? A to the what? P minus n, yeah. P minus n, okay? So I made a mess of that. So now 1 plus x to the p n. Now what's a? If I replace, instead of a plus b, I make it binomial for serious purposes. If a is 1, then that really can be just left out, right? Instead of b to the n, I have x to the n. Now, this is an alternate form of what we did yesterday, binomial theorem. This guy being finite, though, this would only be if you had 1 plus x to the third power. If you had 1 plus x to the 1/2 power, then this whole thing would be kind of crazy, whack, you know. But imagine then, if it was 1 plus x to any power, which could mean roots, then to fit it well, going back to Taylor ideas, if I needed to fit a square root or something, wouldn't I just need to get infinitely many terms to get a really good fit? And so for any case where you have a power that's not a whole number, then you would say instead of a finite going to p, you do infinitely many. You track? And that's actually what I meant to put in the box. I should have said you need to go to that infinity. All right. Are you so far so good? Yes? No? All right. Now, that actually, if you think about this, it matches what we did yesterday. Let's flesh this out a little. If I expanded that a little to see how it matches what we did yesterday, then isn't the first term p choose 0 x to the 0? P choose 0 is P factorial over 0 factorial P minus 0 factorial. Well, that's P factorial over P factorial, and 0 factorial is 1, right? The next one is P choose 1, x to the first. P choose 1 is P factorial over, remember combination. So how do I do the denominator again? P minus 1 factorial and 1 factorial. But if I were to do a little whoosh, doesn't P factorial have P minus 1 factorial within? And so if I did a little whoosh, what's left? P x to the first over 1 factorial. And if I then did P choose 2 x squared is the next term in the summation. P choose 2 is P factorial over 2 factorial P minus 2 factorial. P factorial has P minus 2 factorial in it, but to get that down to its level, you'd have to remove Pn P minus 1. X squared and the 2 factorial. Now you can see that this is exactly like we are getting yesterday, right? It's just a different way of writing. Are you with me? Can I throw one thing at you real quick? Adapting. Would you? I hope you have a little room here. Adapting. If you wanted to estimate the square root of 26 using the binomial series, you would have to do a little bit of tweaking. Think of it like arctangent gets tweaked in the antiderivative, all right? So it goes something like this. You would say, all right, first of all, the binomial series is 1 plus x. Now you wouldn't use an x, would you use then an x of 25? Well, you could, but imagine how freaking big that would be. That would be, you'd have 1 plus 25 to the first and 25 to the second in your series. Are you with me? And eventually the factorial would catch up and start winning, and eventually it would converge, but it would take forever. And you would need just hundreds of terms to get there. Are you with me? So this just takes too long to converge. Instead, you do a little bit of tweaking. Instead, you would call it, let the function be the let the function be the square root of 25, and then factor out a 25. And then you'd use your binomial with x over 25 as each x. And you'd see things would get really small really fast. Okay. We'll finish that. That should be enough to get you going on the front sheet. Have a wonderful weekend. Hey, I gotta say, the bell rings, and I'm still talking to you. Thank you. I mean, most people say, screw this, I'm out of here. Keep on, I'll figure out the time to get caught up. If you have 142 done, great. If you have questions, hold on to it. I will work the keys for everything and put them online so we can get caught up a little. So, to the extent possible, use the keys online this weekend. Thank you. Have a great weekend. I will put those in this weekend. Put them in the basket with the great please. Good luck on your sports, baseball, soccer. Thank you. Have a good weekend.